Are you calling me lazy?
Well, I didn't want to come right out and say it. Hello, welcome to proglangcast. I'm Steve Thames.
I'm Christopher Augustus.
And we are here to talk today about mutability and immutability in computer programming languages.
Both things.
So for definition's sake, right? What is mutability? Mutability is the ability to assign a value to a variable and then to reassign a value to a variable. Some languages, almost all languages allow you to do mutability. There's very few that don't. There's only one that I know of that prevents you from doing it totally, and that's Erlang. What about you?
You said that's the one language you know of that prevents mutability?
It's the only one I know of that you absolutely, under no circumstances, can create a variable that's mutable.
Absolutely no mutation. Well, first I want to say I think it's more than just variables, right? I mean, from the programming syntax point of view, the way you're going to modify data is through a variable or a pointer to some data. I would say mutability also includes any data that the code has access to in any way changing state from one point to another. So mutation is a larger topic than just, a variable being mutable or not mutable.
That's not the way I was viewing it, because you may remember the discussion we had the other day, and I was asking specifically about that question of state. Because whether we want it or not, in a client-server environment, state exists. And we have state that's maintained on a server side. Sometimes we have it on the client side, but very often we have it on the server side. And somehow it has to be maintained somewhere. A language like Erlang presents an interesting challenge because state still exists. And if you're talking about immutability, are you talking about immutability like state altogether, like state that's maintained, for instance, in a database?
Well, I was just trying to clarify the definition of mutation versus no mutation. So you're right. I mean, the whole point of this conversation is we're going to be attacking the issue of, is there such a thing as a program that has no mutability anywhere, right? Yeah. So you start out by specifically saying a program variable, a named variable. Right. I mean, the definition of a variable is a value that varies, although in mathematics it means something different than it does in programming. But you're right? There's state around the program. There may be state inside the program. Certainly there's state in the environment the program is running in. And when we're talking about mutability versus immutability, we're going to address all those aspects, I guess, of just what's visible to the code, right? What's going to affect how the code executes is going to be affected by whether state that it reacts to, responds to, acts upon, undergoes mutation, meaning it changes over time, or it doesn't change over time. I guess immutability literally means constant, right?
Yes. From the point of view of talking about variables, yeah, absolutely. Something that's, so in some languages, like in C, TypeScript, I guess ES6 JavaScript, anything denoted with const is immutable. You can set it, you cannot reset it under any circumstances. As I said, in Erlang, that's all of them. Everything's a constant. You can't change any value assignment in Erlang. You can in Elixir, but it gives you a big fat warning and says, hey, you shouldn't be doing this. I was looking earlier at a video about Python. And it's interesting because the guy in the video is talking about how Python has immutable strings. The way he demonstrated that was he said, okay, here's my A equals string, right? And then he printed it out. And then he did A equals another string, which worked fine. And he said, but strings are immutable, and here's how you know. And he showed, in both cases, the address of the variable in memory. But as far as strings are concerned, if you reassign a string anywhere, it changes the location in memory, especially now, because in the old days, like with fixed length strings that we had to deal with in, say, Pascal and C and assembly language, that kind of thing, then you could individually change the same area in memory. But as we've created dynamic strings going further with later languages, then every time you assigned a string, you were reassigning that location of the string. Am I right about that?
Well, what is assignment? In some cases, it's a rebinding of the name that is being used in the code to a new location.
To a new location.
Or is it a modification of the data in memory currently pointed at by that name? Rebinding would basically say, given this name A, if I reassign a new value to A is no longer pointing to the original data in memory. It's pointing to some new data in memory, meaning that data in memory remains constant. It does not change value. Now, I can no longer access it through A because I've rebound A to some other location. But anything else that was also pointing to that same memory location is unaffected. It's not going to experience a change of state.
To my mind, binding is where we say this symbol, okay? Anytime we access that, it's going to give us access to a value reference somewhere. We have bound that symbol to this particular area of memory that has this data. In some cases, we can rebind them. So in the case of an immutable language, something that's totally immutable like Erlang, that's not possible. There is no rebinding. When you set A is equal to 10, A is always going to be bound to that area of memory that has the value 10, and that's it. You can't change it. If I take A and I assign it to a tuple, okay, let's say I assign it to a collection of values, it's still, once again, it is now pointing to or bound to an area of memory that has this tuple, this collection of data, and I cannot rebind it. Anyway, that's that. I just wanted to start with that, with what we mean by binding. There are languages that make a specific distinction between primitives and references, are saying this is a primitive. When I pass it to you, you're going to get a copy of that value. And that's important to understand. When that value is passed around, you're getting a copy of it. You're not getting a reference to it. Copy.
Well, that's a very important distinction across programming languages, especially in the object-oriented era, where they'd say value semantics versus reference semantics, pass by value, pass by reference. And in C and C++, we always know exactly whether we're passing an argument into a procedure by value or function, because the syntax incorporates that. In C, the only way to pass something by reference is to pass a pointer. There's a star, there's a symbol, you know, I'm giving you a pointer to an address. If you do anything at that address, you may be modifying memory that I still point at, that somebody else still points at, because I gave you the pointer in the first place. Or if I call a function that allocates memory and it gives me a pointer back, suddenly I can do what I want with this, and you may also be pointing at it because you knew what it was in the first place. So we're sharing an address.
The ability to change data and have data that you are managing changed by something else. That's what a mutable environment allows.
I think there are two aspects to mutation, as you've already started describing. Rebinding, meaning changing what a label now points to, which from the point of view of code using that label, using that name of that variable, will see that as a change of value. But the actual location that was originally assigned is not modified. And then the other side of mutation, which is much more dangerous and insidious, is actual modification of the values pointed to by a label. We are modifying the location, and anyone else that also directly or indirectly is looking at that location is going to experience mutation. So we do need to talk about both things. We need to talk about rebinding, which usually doesn't affect anything outside some lexical scope, whereas mutation of the location itself can be totally across anything within the same, that has access to the same memory, meaning anything within the same process in most operating systems.
I think when we talk about mutability, there's something else to be really clear about. When it comes to a computer, except for what we call read-only memory, there's nothing that's immutable. Okay, memory is mutable. You can write shit to it unless it's at the hardware level, one-way memory, read-only memory. Then you can change it. It's the language architecture that prevents you from doing that. For instance, when you're coding in machine language or assembly language, you can change anything you want. That's nothing but a handful of scalpels.
So this comes up, by the way, this issue you just brought up comes up in iOS programming. Whenever I want to do stuff that's dynamic, I always do iOS first because it's the most strict environment. And here's one of the rules that goes into an iOS app. You cannot execute code outside of the already built code segment, meaning you cannot upload new code to it. Like you can't have an iOS app go out and load code and execute that code.
Programmatically.
It prevents that from happening. They actually do support the execution of JavaScript as a special case, and it allows for hot reloading of code. Once you've published your app on the App Store, you can provide app updates over the wire, but you can only do that with JavaScript code. That's a case in which there is some enforcement of immutability, at least in terms of code data, not necessarily variable data. It's such a significant decision. It's one of the biggest selling points to React Native.
Sure.
Because React Native is saying if you write your application code in JavaScript, you can push updates over the fly without going through the App Store. If you do it in Flutter, if you do it in Swift, if you do it in Objective-C, anything else, all your updates are going to have to go through an App Store release. It's a big selling point and why a lot of people will use React Native.
Okay, and that's a good point. But when we're talking about manipulating data in a program, the only thing that prevents you, not code, the only thing that prevents you from modifying that data anywhere is the language you happen to be using. So the Erlang is totally immutable, and once you bind a variable or a value or symbol or whatever you want to call it, once you bind a symbol to a piece of data, you cannot rebind it. You never are modifying values directly. You are always transforming them all the time.
You take an input, you produce a new value as a result, not modifying anything that becomes input to you. You're yielding a new result that is a transformation of that value. So there are other languages, of course. The ones I know of, I don't have deep experience of, but I know of in my head: Haskell, Idris, which is based mostly on Haskell, Elm, inspired by Haskell. So these are all kind of in that.
Did these all disallow mutability?
And then Rock, the new language by Richard Feldman, again inspired by Elm, which is inspired by Haskell, based on Haskell. Yes, these are the languages that are strict about not allowing mutability of variables. But to your point originally, obviously mutation is happening somewhere around the outside of the core of your programming, right? In the shell, in the UI, or in the database, on the console. So there are mechanisms within the language to manage that mutation. But for what you're saying, if you just declare a variable and you assign it a value, it can't get a new value for whatever scope that it's in. I don't know if it can be rebound, but if it gets aliased, meaning if I assign A and I assign B, even if I rebind A to something else, B is still going to point to a constant value that cannot change, right?
If we talk about aliases, then here's what alias says to me, is that A and B are both aliases for the same location.
That's what it means.
That's where it gets confusing to me, because in that case, in C we call it a pointer. There's no such thing as an alias. It's a pointer. And to my mind, that's a better description. It's a pointer or a reference.
No, but that's important. The reason alias comes up, this is a very important part of the design of Rust. If you declare a variable in C, which is the simplest, you have two types of variables, as you pointed out. You have primitives and pointers, right? So you either have a primitive or you have a pointer to a primitive.
Mm-hmm.
The pointers are aliasable. You're right.
Yeah.
If I say C is a pointer to a byte, and then I say D is a pointer to a byte, and D is equal to C, they both point to the same location of that byte in memory. If I say C is equal to this byte, like 5, and then I say D is equal to C, D is getting the copy of the
Copy.
value C. It's not an alias. They're not pointing to the same location. So the only way to have aliasing in C is with a star, with a pointer. And that's why so much of the code is pointers. Strings themselves, to your point of the pointer, is not a primitive. It's a pointer to a byte, and it's assumed that that string is defined by subsequent locations of bytes in that same, starting at that offset until it finds a 0 value byte, and that's what defines a string, and all the string operations are oriented around that.
But again, mutability and immutability is only defined at the level of the language. Clearly, it's designed to protect the programmer from doing something stupid, okay? Like changing state. Now, in an imperative environment, obviously, there's great virtue to mutability, because then you can just take a variable and say it's equal to this and change it to this and do this to it and this to it. Now I've got my resulting variable. In an immutable environment, every stage of that transformation has to be a different variable. Let me give you an example. In this one that I just finished, what it does is it pulls out a section of a piece of code, and it removes any comment delimiters. Then it reformats into something readable, then replaces comment delimiters, and then tabs it out to the indent size, and then inserts it back in the code. So you got 4 or 5 different steps of how that piece of data is being transformed. If I'm doing this imperatively rather than declaratively or functionally, then what I'm doing is I've just got const equals this, const equals const, all the way down 5 or 6 different variables. I did something yesterday with promises. Well, kind of a low rent chaining of data used a promise because they don't have a pipe symbol in TypeScript. So you can't pipe the data from one location to another. So this was another way of doing it. And the reason I make the point is because one place that immutability has an impact is in debugging. Because if you're doing a transformation in an imperative way like that, signing a value and then signing another value based on that value, transforming, then you're going to have to watch a lot of variables to see every stage of that change in the debugger.
Oh, you're saying mutability helps debugging?
Well, it is one advantage in an imperative environment. So this is what I'm talking about. In TypeScript, I've got a promise that's resolved with my original text value from the code. Then it goes through another one using text. My function input is text, and it calls a function called uncomment block passing text. And then that's chained to another one where I bring in text, and then I'm going to reformat it. And it's chained to another one with, and text is the name of the value in each function, but it's not being reassigned because I'm passing the data into a function and taking that as a parameter. So each one of these is a different lexical scope. And the debugger won't care. It sees text is text. Okay, text is available here, so it'll show me. And that's how you can do it.
So you're using promise to create your own pipe.
Yeah.
Because what you want to do is you want to do effectively the B combinator. You want to just pipe. You want to say, I want the output of this operation to be fed into
the input of the next.
And it's always one argument in, one argument out, one argument in, one argument out. In F#, you can simply use the pipe. In Elixir, you can use the pipe. I don't know if there's anything else. I think Haskell has some kind of way of combining with the same pipe. So you're using a promise. Promises are usually used for asynchronous, but you're not using asynchronous. You're just using the chaining effect.
I'm using the chaining effect.
In Kotlin, they have what are called scoping operators, which is a let, a run, an also. What was the other one? There's like 4 or 5 of them. And you do the same thing to fake the pipe. You say let was the same as then. And instead of having to name the variable, it's implicitly called it. So inside the scope of every let bracket, which would be what you're calling text, it would already have the name it. So you just refer to it. You just say it. If you want, you can give a different name. You could say this instead of it, but it by default has it. And that's the way I fake the pipe.
I actually like it this way. It's very clean, and like I said, it helps with the debugger. But when you look at the code below this one that I've got commented out, where I've got const input is equal to the text from the document, then cleaned is the one that gets uncommented, and then const formatted is the formatted version, and then commented is. If you want to do things immutably in an imperative environment, you have to do it this way. Okay, there really isn't any choice. You're just going to have to assign multiple variables because you can't reassign.
I'm curious, which do you prefer? The named variables or the thens?
I don't really see the value of having 5 different variables that represent the same input in a state of transformation. So that's what I've got with my resolve up here. Every then is taking in a function that takes one parameter, and that's got the same name through every one of them, but it's just like a pipeline.
But the difference is the named variables are providing documentation. Input, cleaned, formatted, commented, and indented.
I agree.
It's describing what each step is doing. And in fact, I've definitely worked on teams where they absolutely insist that the named variables are extremely useful because of that. I'm with you. I like the thens, I like the lets, I like the pipes, but it is self-commenting through the names of those variables. It's commenting what's happening at each step.
And I know that in some cases we disagree on this point.
Well, not necessarily. So I would take a different approach to documentation. So for example, let's look at the thens above. It's actually half documented.
Yeah.
Like, for example, the first one, you say uncomment block. You're calling a function named uncomment block. I definitely would prefer commenting via a name of a function or procedure over an actual comment that says this code means uncommented or this code means formatted, simply because there's no enforcement of that. You could name what's going on without using specifically an actual comment, an actual language comment. But then somebody would just argue like, well, how's that better than having a named intermediate variable? And I don't know the answer to that, other than one's a functional style versus the other.
I prefer it this way. I prefer the chaining.
I agree. I don't like intermediate variables because even if they're immutable, they represent another piece of state that's sitting somewhere that I have to think about. These const input, const clean, those things all live to the end of this lexical block.
They do.
Whereas above, uncomment block right there, the resulting value of that call only lives from its result to being passed in as the input to the next. There's no lexical scope beyond that. And I find in programming, the more you can limit lexical exposure, it's better. It is one of the benefits, whether you're mutable or immutable. I agree that if the more variables can be immutable, the better, and the more narrow your lexical scopes, the better.
And that's the great value of the transformation pipeline. Everything is intermediate. It's immutable. You have one input, you have one output. And I really, really do like that. I like this kind of structure. Depending on the language, some of the languages really lend themselves to immutability. Maybe they do have a mutable structure allowing you to change variables, but they've got processes that make it a lot easier to do this kind of recursive thing or pipeline type of thing to where mutability is not required.
So it's funny you say that. And we're going to take a little bit of a detour for just a moment. I was thinking earlier when we were about the topic here, immutability, and I was thinking about paradigms. There isn't an immutable program or like named paradigms. So we have procedural programming, functional programming, object-oriented programming, logic programming. What else? Array programming. There isn't one called immutable programming. When we think about immutability, we tend to usually think about functional programming, and people that would say something is in the category of functional programming, one of the bullets they would say is immutability is important. But we found examples where that's not the case. For example, the Lisps don't really put an emphasis on that. Their emphasis is on being able to pass functions around as values. That's lambda calculus. But they support mutation. Even though it's considered non-idiomatic to code that way, they support it. So it's clearly not a high enough priority to restrict mutation. So until you talk about specific languages like Haskell, like Erlang, like Idris, like Elm, like Rock, and others, maybe some of the proof languages, not all of functional programming, Clojure, are going to say total blocking of mutation is a requirement. So what other paradigms does it live in? I would say absolutely depends on mutation. OO says we prioritize encapsulation, and in doing that, we sacrifice immutability. You can't really do a mutable object-oriented program. People talk about doing it, but I've looked at it and it's like,
it's hard.
It
I tried doing it
depends.
too. It's very hard to do.
It depends on mutation.
Mhm. It depends on
Right.
state, and
So
state has to be mutable in that kind of an
it is
environment.
literally saying your program is this encapsulated state all over the place, right?
Mhm.
Functional programming says our priority is functions as first-class values. And the other thing they say is functions are separate from data. Actually, I would say that's the number one priority. It's the opposite of OO. OO says functions are methods on state. State and operations are bound together. That's fundamental to OO. Functional programming says, no, no, no. Our fundamental thing is they're separate.
Yeah.
They're separate from each other. Okay. Procedural programming, what is its number one priority? It would be, I was thinking about that today. I mean, what would you think would be, if you had to say what defines procedural programming, the ability to break down code into procedures?
You mean structured programming, right? But that's what you mean by procedural?
The idea of structured programming didn't hit us until C and Pascal. And the whole point of structured programming was eliminate go-to. You don't go to something,
here's
call it by name, and it returns to whoever called it. And thus your program consists of separately structured procedures. There's another factor to structured programming. I kept saying getting rid of the go-to, but it was lexical scope. Lexical scope was a new thing because BASIC is global. All the variables are global. APL, all the variables are global. So structured programming introduced the idea of
subroutines,
of subroutines that have lexical scope.
See, that's where I would break it up, and I would say that's procedural. I think where you had lexical scope, that's where you had procedural programming.
I think that's it. I think lexical scope is the priority of procedural programming. Now it's embraced by other paradigms later, but it was the strong thing. It was like we lexically scope, and I believe that begins with Algol. So I think Algol was the first kind of truly like procedural structural language that said we have lexical scope, and then Pascal picks up on that. C picks up on that. Mm-hmm. Other languages pick up on that. So that's the priority of procedural programming. Does it take a position on mutability versus immutability? Rust, the paradigm that Rust strongly embraces, is procedural, not functional, not OO, not array, not logic, procedural. And everything you declare is immutable by default.
By default,
it allows mutability, but it's optional. You could write code that isn't. Now, the main argument that I think people make against needing mutation is not semantic, it's practical. It's always, yes, I could do stuff immutably, but it's going to perform badly because I'm constantly making copies of values. I'm not changing values in place, meaning I'm paying the overhead of a copy operation. I'm producing a new value, which adds overhead. If you're in a garbage collected language, the garbage collector will do a new allocation, and then at some point it's going to free it. That's overhead.
Well, think about Erlang, for instance, right? Erlang is garbage collected, right?
I know.
So
it's one of the reasons Erlang's not recommended for high performance aspects of the application.
And yet
plug in Rust or C.
Yeah, and yet they built it to handle our telecommunications requirements back in the 80s, and computers didn't process that fast, but it seemed to manage to do the trick. So
because at the speed of I/O, it's fast.
Yeah.
At the speed of crunching a table of 1 million rows in memory, it's incredibly slow.
Yeah.
So it depends on what you're doing. But I'll give you an example of garbage allocation overhead. Before WebAssembly actually came out of a thing called Emscripten. Have you heard of this? In ASM.js?
Yeah.
ASM.js was a way of trying to make JavaScript code super fast in the browser. And the main way it did that is by allocating a giant array of integers as a pre-allocated block of memory, and then doing all of its own micro memory management inside that without going through the normal garbage collector of JavaScript in the browser. And that's what made it so you could take C++ code like a 3D game It gets compiled into this ASM.js representation. Everything just becomes these integer operations. And then it just reads and writes and reads and writes and reads and writes and reads and writes. And that is a significant performance increase simply because in the browser, JavaScript's normal garbage collector adds a lot of overhead.
But let's talk about, getting back to the question, when I watch videos about, or I read about mutability and immutability, you get a lot of, well, this is immutable, sort of, because you can change it here. Like the example I gave you in Python, where he says A is equal to quote Steve quote, and A is equal to quote Christopher quote. To my mind, that's mutable, but they're going to tell you, no, that's immutable, and here's how you know, because I can't change the first character of the string, Steve, from S to C, because then it'll give me an error, because I'm trying to change an address of memory. If I'm going to change the whole string, then that's rebinding. It's actually changing A to point to another location. But I don't think the average programmer is either going to know or care about that. They're just going to say, well, that's mutable. So when they say stuff like this string is immutable, but it is rebindable, I'm like, come on. It's mutable if I can reassign the symbol.
Let's actually separate those into two categories. Let's call it lexical mutation, which is rebinding, meaning the same name within the lexical scope gets reassigned to something else. It's rebound.
Right.
A had this value at this point in the code, and the same A now has a new value at a later point in the code. So that's lexical mutation.
Right.
Then let's call the other thing location mutation. Whatever that thing points at, its location is mutated, and that's where aliasing burns you. Lexical mutation doesn't have the aliasing problem. But with location mutation, if A is Christopher and B is assigned to A, and A is Frog, B is now Frog, that's location mutation. That's been aliased.
I have a hell of a time with the term alias because it abstracts it out too far. That's why I prefer pointer or reference.
I'm just telling you, in the PL space, alias is very much used, especially in Rust, for example. Yes. In a description of the language and people talking about the language, that term is used frequently.
I get it. I remember when I was learning C, and I got pointer right away. I mean, that was a no-brainer, okay? I've got a primitive, and I've got a pointer to a primitive value. I didn't have any problem understanding that at all. If somebody had said alias to me, I would have found that confusing. I mean, at least I think I would have.
A second name for the same thing, or a second name in a scope to something in another scope. It basically means what I'm saying, shared location.
Mm-hmm.
From C, we had pointers. You either have, you're right, primitives and pointers to primitives. Now C++ comes along and adds the ampersand. It meant this is a reference, not a pointer. So now you've got a new term called reference. C++ said, we need these immutable pointers. A reference is a pointer that can't be null and it can't be changed within its scope. You can modify the thing it points at, but you can't modify the pointer value held by that variable.
It doesn't sound to me like there's any difference between a reference and a pointer other than a compiler difference. The compiler says, we're not going to let you do that. This one, if you want to be able to modify that value that's passed into you, then you're going to have to call it a pointer. Because if you call it a reference, then we're not going to let you change it. What are the advantages and disadvantages of mutability and immutability? You kind of alluded to this question earlier. When I start looking at the issues of mutability, it's a challenge to really think declaratively and to think functionally, to think in an immutable way. For a lot of people, it's hard to think that way. I mean, I had to watch a few videos. I find myself now looking at code that I've written imperatively and object-oriented. Like when I was writing this particular tool that I was telling you about, the VS Code thing, because that's pretty much the same piece of code for the last couple of decades. I wrote it a long time ago, and I keep implementing it in other editors that I use. And there's a couple of sections of the code, specifically in the formatter, which goes through and reformats the text. That one was really tough to figure out how I would write that. So I kind of gave up on it and said, well, I want to implement this. I'll do that as an exercise later to see if I can do it. Because it's hard. It's hard to get your head around it.
My first bye-bye hello world in Scheme, what did I do? I mutated, right?
Yeah.
And in the last episode where we showed our refactorings, it took extra work,
Yeah.
extra effort to make it immutable, but it was totally doable.
Yeah.
I guess my excuse can be I'm not as practiced at doing a lot of scheme programming, but the easy thing to do was to make a local variable, or not even local, right? The first ones were global. I was like double sin, right? I needed to be triple, double punished for that.
Well, at the time,
I made global variables and I mutated them.
Yeah. But at the time, we weren't trying to address the issue of mutability specifically at that time, though.
Okay, fine. All right. We could use that as a defense, but I was representing BBHW, bye bye hello world, in scheme. I'm supposed to do that idiomatically. And somebody burned me on Reddit deservedly. He's like, yeah, I guess so. It's not really idiomatic to do that, but the language allows it. It gives you the set bang. And what's funny is when you look at scheme in particular, which is a functional language based on lambda calculus, which is the foundation of functional programming, right? From Alonzo Church. And the main introductory text that I was exposed to was SICP. He doesn't really talk about immutability in there. He talk about functions a lot. Functions, create functions, lambdas, and all that. But again, we think of immutability being an important ingredient of functional programming, but there is a world of functional programming where they don't care that much about it, it seems.
There's no denying that if you're going to require immutability, that you're going to add more work. You're taking away the ability to change something in place. When we talk about Erlang, for instance, was it Robert Verding? When he originally wrote that, he made everything immutable. You can set values, and then you're just going to have to pass them around to different things that are going to do something with the value. But you can't ever change them within one lexical scope. It looks to me like the big concern we have about mutability is that the data that we're working with being changed in someone else's control that we don't know about. So that what we're expecting to have, we don't have.
Okay, so let's go with that. A bunch of programmers, and I did some reading before we came in here, would say, well, that's no big deal. Why is that a big deal? And in fact, this is, I'm going to push back against you a little bit on the past. There are times when you'll say, this requires discipline on the part of the programmer. I don't think the language should give me guardrails or straitjacket me into doing this. But this is an arena in which we're saying the language should or should not have a restriction, should not or not block us from doing this thing. Versus someone would say, well, if the programmer's just disciplined about, they know how to do mutation properly and not have to worry about it, right? That would be an argument somebody would say, if you're a good enough programmer, it's no big deal. I'm going to give you my answer. What's the danger of mutation? The longest, most difficult times I've ever spent debugging problems in code was always, how did this value get changed?
Right.
Like, this is the wrong value, this thing, where the hell is it getting stepped on?
Right. What
is happening, especially in multi-threading, right? Especially, any UI-based thing is multi-threaded because you have a UI thread and you have UI IO events coming in independently. Mm-hmm. So have I spent more time chasing down those problems or having those kinds of bugs be a problem in code than the amount of time it would take me to add the effort to code immutably? I don't know, because trying to code totally immutably is a new thing for me now.
Yeah.
I've been doing it for a couple of years, and I mostly be doing it in languages that don't require it, but provide it as an option, like Kotlin, like Rust, where they'll allow you to mutate, but I'm using, to your point, my own discipline to stick to non-mutable types, to constant types. In my C++ code, I started just consting everything. Has that taken me more time than the trouble I've gotten where I've been burned by mutability being there and as a default? I don't know.
Yeah, here's the thing. If you're in an immutable environment, everything's const, then from the moment it got assigned, you know exactly what it is. It doesn't matter what environment you're in. It's going to be that value every freaking time. Okay.
The ability to reason what the code is doing.
Now that is one powerful value of immutability, even within the same lexical scope. If you're going to write functions where maybe you got 20, 30, 40, 50 lines in a function, you're going to know what every variable is all the time. So I would say that's a great advantage and will always save you time on the other end. The argument you were making is, has it cost more time on the back end trying to debug those problems than it is to learn them? I'd say absolutely. I will take the time to learn how to do it immutably up front every time because it's always spent more time.
Yeah, not even more time, but is the fallout more serious? Mm-hmm. So like it could take less time, but the potential for a disastrous problem in the code, in production or in use or whatever, something failing is much greater. Doesn't matter that it takes more time. You have riskier software. Mm-hmm. Like, does it increase the risk of the software to have more mutability? I'm going to come down and say definitely. Yeah. Definitely the least amount of mutation going on in our code, the less risk we have of it working improperly in general. Yeah. I'm going to make that statement. It's interesting that Erlang made a decision very long ago when it was created, which is the 80s.
Yeah, mid-80s. Right? Yeah.
Mid-80s. Okay. But programming immutably, at least in my radar, didn't really come onto the scene as a big deal until the 2010s with the advent of multi-core processors, mm-hmm. where now multithreading was no longer like a luxury or like it was more of an extra feature.
Yeah.
It just became the natural way of things happening, and suddenly software was just failing constantly because shared mutable state across threads is the worst scenario of mutation because of race conditions, right? Not only are you sharing mutable state, you don't know where it's happening or who's touching something first. And this is where we're seeing the rise in the 2010s, or the rediscovery of functional programming mm-hmm. that was dropped decades before, held onto by Erlang and Scheme in the periphery, but in the mainstream didn't care about it. Yeah. Now suddenly it's like, oh my God, I can't take this algorithm and spread it across the cores because the algorithm is using mutable state. Yeah. And as soon as I put it on multiple cores, I get race conditions everywhere.
Sure.
It's all messed up. So now they're saying, functional programming with immutable state is now very valuable because I can take an algorithm and I can suddenly multiplex it across these cores, get that performance benefit, and not have to worry about the unpredictability of the results, right?
Yes, but I think that, first of all, the rise of I think what you're saying is the rise of the requirement of multi-threaded thinking, because
the importance of it.
We were working with different threads and different processes all the way back in the days when we were doing just client server architecture. And we did have some shared state in those environments.
Well, the race conditions weren't as bad until the 2010s. And the reason is there's only two forms of concurrency happening prior to multi-core processors. There's I/O concurrency, asynchronous operations, right? But the concurrency happening within a single core CPU is fake parallelism. It's not true parallelism.
That's true.
Right?
It's time sliced. Yeah.
It's either dispatching logic based on I/O boundaries, asynchrony boundaries, right? Waiting for something and then doing it, or preemptive multitasking like in Erlang, where it preemptively pulls out a task, gives another one control, pulls out a task, and you can't predict where that's going to happen. At least in asynchronous, you can predict where the yielding is happening because you're basically either doing a wait or you're doing a yield. Like within the code, as the discipline of the programmer, I'm vulnerable to a race condition because I'm now yielding at these various points. As soon as you get into multi-core processors, you now have parallel processing.
Yeah, true parallel processing.
Fake, actual execution happening in parallel by two cores accessing same locations in memory of the same shared memory bus. Now the CPU is managing, obviously a write here and a read there, one's going to be behind the other. But from the point of view of the code, it's simultaneous.
Right.
And there's no knowing who's going to come first and who's going to come second. And what they found is when they tried to embrace all the same synchronization controls you had in fake parallelism, right? When you use mutexes and all that sort of stuff, the performance just went to zero.
Yeah.
So it's like you had all these multi-cores, but they're spending all their time in concurrency control, not doing their work. And it was like, well, how do we get around this problem? Oh, functional programming, where you start an algorithm, you pass its data, and the data that it operates on that's shared never changes for the course of the algorithm. Right. So it just does all of its crunching, like super high speed. It's got its own state that's not shared with anybody. And then it produces a result, and then those results are aggregated up. And that's where you get map reduce and the things that the array programmers excel at that will scale up with multiple cores, whereas everything else just craters with multiple cores. Well, I think next time we address this topic, we should now talk about where in the application mutation has to live, because it has to happen somewhere. Because at the end of the day, if you're a word processing document, the document's changing. That's a mutation of state. And how do you cope with that, with this idea that we seem to value, that we should write as much of our code using immutable state as possible, immutable values and variables as possible. But at the end of the day, somewhere there's mutation of state. How do we reconcile those things?
Okay, well, listen, that's it for today. That's our discussion about mutability and immutability. Hope everybody's enjoyed it. And I think we're probably going to be doing are you still working on K for Bye Bye Hello World?
I haven't touched it, but I need to pick it back up. I think that's my next objective, BBHW and K. So I think, let's shoot for that next time around. And
I'm going to be doing LFE. Now that I've got this thing that I've been working on, I'm going to be doing LFE next.
Yeah.
Well, that'll be for in the weeks to come. So thanks everybody for joining us. Till next time.
Yeah. And when you're dealing with mutability, I wish you the best of luck.
Happy programming.